Please.
Okay, so here's the first big unit, which is on circular motion. So the first thing we have to decide is that as things go around in a circle, so like if I take this rubber stopper and I swing it around over my head like this. So here's the first $1 million question, is that once I get this thing up to speed, okay, so once I get it up to speed, is it accelerating?
No.
Yay or nay?
No.
Yes.
Pop, you say no, it's not. Why?
Because it's going the same speed.
It's going at the same speed, so therefore it's not
Velocity.
accelerating. Okay? Now, this side over here says it is accelerating. Why?
Velocity vectors are constantly changing.
Okay? So, let's go to the back and do a quick little demo. So, let's bring it down. I'll just keep it going.
We need to go.
I could win.
I'll say. I'm gonna wear black shorts. Everybody bought them.
I'll just bring both of them. I have a feeling I'm wrong. No.
Okay, so here's what we've got. Current like this, boom. And this is what's known as a liquid accelerometer. Because oddly enough, it contains liquid and we use it to measure acceleration. Okay? Leave my magnets alone. So what I'm going to do is I'm going to put this on here. And I've got a string attached to the end of the string, or to the end of the cord. And I'm going to put a, I don't know, 50 gram mass on the end of it. So I have this, like this, like this. So let go, okay, it's going to accelerate. We'll put this up here like this. So when I let go of this thing, there are three things that could happen to the liquid inside of it. What's one of them?
Move forward.
It moved slosh towards the back, okay? Slosh is a highly technical term, okay? What's another thing it could do?
Slosh forward.
Slosh forward, okay?
Same place.
Or it could just have no slosh.
Yeah.
So slosh forward, slosh back, no slosh. So what do you think it's going to do?
Slosh back.
Slosh back, okay? Let's do this,
Slosh. Yep.
okay? And oddly enough, it
Slosh.
sloshes back. Why?
Inertia.
What about it,
It's not.
Mr. Wolverine?
It doesn't, or objects at rest have a tendency to stay at rest. So when the cart starts moving, the liquid has a tendency to stay back before it moves
Okay?
back.
It's beautiful. Okay? Spot on explanation. The water inside has mass.
Are you gonna solve that?
The water inside of that has mass. It doesn't want to move. Now, visualize this if we could do this. Imagine that I could let go of this thing, and at the very instant that I let go of it, I can make the back section of this disappear. Okay? So I'm going to let go, the back section disappears. What would the water do?
Stay in the same place.
Yeah. Now, but here's the big question. When I let go of it, is there something in front of the cart pushing it towards the back?
No.
No. This is going to be important, okay? There's nothing in the forward pushing it back. It just wants to stay in place, right? Now, goes back to this whole idea of what happens when an airplane takes off, when your car accelerates forward. So if you're sitting here, you're going to think, oh man, I was pushed back into it. That's not what's happening. There's nothing in the front pushing it. What you feel, if you were the water, you would feel an action-reaction because you're feeling that back section pushing on you to make you accelerate because you don't want to. So you're feeling that action-reaction. Now, here's the big idea. When I let go of it, this is simple, but it's going to be important. When I let go of it, what's the direction of the acceleration vector? This way, right? Which direction does the liquid move? Opposite direction. Okay? So this is going to be important. The level of the water moves in the opposite direction of the acceleration. Okay? Now, that was with a 50 gram. What if we put a 200 gram mass on the end?
It's gonna slosh more.
Slosh more violent.
Why?
More acceleration.
Yeah, more acceleration and it wants to.
So with more acceleration, does that mean that the water has more inertia?
No.
No, it's just more force.
Okay, more force because it's accelerating
Faster.
Faster.
faster. Okay? So now when I let go of it, whoo! Okay?
Oh,
Damn.
So here's what I want you to see. The steeper the angle, the
bigger the
acceleration. Right? Got that? Okay. Now, keep that in mind. So now let's go back up front.
What is that in there, Mr. Burkhead?
It's just water.
It looks kind of like blood.
Yeah, no, everybody asks is if it's like the blood of freshmen.
Does this have anything to do with Mrs. Wilson?
No. Ma Walston,
The side of it says from Tyler Wilson.
that's her brother.
Okay.
Her brother made this for me.
You want me to sit in the
You got 5 minutes. Are we gonna learn anything in the next 5 minutes?
The math.
Kinda, yeah.
Learn all this.
I mean, but there's so much to go over today, though.
We're gonna have to watch the lecture.
Yeah. Okay, Jackson, come up here.
Okay.
Oh, that looks
So Jackson,
it looks like it's shaking.
this out.
Looks like it's bending.
Okay, no, like that. All right. All right, so here's what I'm gonna do. I'm gonna spin Jackson around, okay? Now, if Pop was right, and objects that move in circles don't accelerate, what should the water level inside of here do?
Stay the same.
Should stay completely level, okay? So there's 3 options that are gonna happen when I spin Jackson. Option number 1, it's gonna slosh out. Option 2 is gonna slosh towards Jackson. Option 3, nothing, no sloshing at all, and Pop was right. Okay? So out, in, flat. Flat. So how many vote is gonna go out? You don't know.
Well, I was just being contrary.
Okay, how about nothing? Anybody on the inside train?
No.
Okay, so you ready? So hold that out a little farther, out like that. Okay, you ready?
Yeah.
So I give this a spin. Lo and behold, he goes towards the outside. Now, as he slows down, what happens?
Starts to
Starts
It
level out.
levels out. So what's the relationship between acceleration and velocity? The faster you go,
The more acceleration.
the greater the acceleration.
No.
Now, here's the important thing. Hold that back out. Which direction was it sloshing?
Oh wait, no.
Sloshing out. So what's the direction of the acceleration?
Inward.
center.
Inward, towards the center. Okay? So this is why, thanks sir, I got it. This is why it's called centripetal acceleration. We're good. Got it? So I know it's a comfortable chair. So the reason that we call it centripetal acceleration is because centripetal comes from the Greek word meaning inward seeking. Okay? So when you're talking about centripetal acceleration, okay, there's 2 things I want you to remember about centripetal acceleration. Number one, it always acts inward towards the center, okay? The second thing is that it acts at a right angle to the velocity vector. So what that means is that when I take yonder rubber stopper and I swing that thing around over my head, okay? The rubber stopper is accelerating because of the fact that when you talk about velocity, and someone said this earlier, velocity is a vector quantity. So what two things does it have?
Magnitude and direction.
Magnitude and direction, right? Now, up to this point in time, up until October 13th at 1:39 in the afternoon, the only acceleration we've ever talked about has been changing the magnitude of the velocity vector. Is it speeding up? Is it slowing down? Okay, is the velocity vector constant? Okay, so up to this point in time, our accelerations have been defined based upon a change in the magnitude of it. Now we're going to switch it. So now we're going to keep the magnitude the same, but now we're going to change the direction. So as this thing is going around, okay, going around like this, cool with this? Now, here's what's going to happen. I know that it's accelerating because if you invoke this Jedi stop the force and watch, as soon as I let go of the string, what's it going to do?
Fly off.
It's going to fly off, okay? Because if Mother Nature liked circles, when I let go of it, this would be really cool. If Mother Nature liked circles, when I let go of it, what would it do? It would keep going around in a circle, which would be cool. Okay, you could walk down the hall and things would just keep orbiting around you. Okay, it would be kind of cool, right? But by virtue of the fact, good luck, gentlemen, by the way.
Thank you, sir.
So is this like substate, regional, normal league?
That's,
This is the toughest game of the year. We're playing Life Prep.
Playing what?
Life Prep.
Okay. All right.
I thought they were a church.
They're bad.
They're what?
They're bad.
Are they?
They lost to the Homeschool Alliance.
Okay. All right, well, good
Wichita
luck.
Homeschool Alliance.
I'll send you all the video.
If I'm being honest, I'd rather be here watching the lecture.
Okay. You might not get it till tomorrow, but I'll send it out.
No worries.
Okay, all right, good luck.
Thank you.
Okay, so here's the deal. So at any given point, this rubber stopper wants to travel in a straight line because that's easiest. Because if you look at Newton's laws of motion, first law of motion is inertia. And there's two parts to that. It says that it wants to maintain a constant velocity. That velocity vector has two components. It has magnitude and it has direction. So if you're changing either one of those, that requires a force. So, because the direction that it's changing is always inward. So we're continuously pulling this velocity vector inward. So that's why that force, okay, and we're going to put F sub c, which stands for force centripetal, is acting inward. Because at any given instance, that velocity vector wants to take off in a straight line. So, just like F equals ma in linear, same thing happens in circular motion. So, centripetal force equals mass times centripetal acceleration. So, just like if my velocity vectors are changing in a particular direction and a certain acceleration, the force has to act in the same direction as the acceleration vectors do. So there's two things that are acting inward. Your centripetal acceleration vector is pointing inward, and your centripetal force vector is pointing inward. Okay. So visualize this. Let's say Vanessa has a Jeep, okay? And here's the steering wheel, okay? Here's Vanessa, here's the rear view mirror, and she has the pineapple thing hanging from the rear view mirror. Okay, all right?
The pineapple.
Now, Vanessa initially has a door, okay, right here. So she's there. Now, she's going to take a hard right turn. So imagine that you're here, right? You're driving.
Yeah.
And you're going to take a hard right turn. Vanessa, what are you going to feel inside of that car? Yeah. Yes. So here's what's going to happen. Vanessa is going to feel like she was pushed against that car door.
I have a real life example of this yesterday.
Okay?
My friend has these like golf cart things because they're not like actual golf carts, but that's what she calls them.
Okay.
Her sister was driving and she flung a left and I was on her right and I fell off. I sprained my elbow.
Ironically, it freaked above inertia. There you go.
Yeah.
Okay. So here's the deal. So what's going to happen is, assuming that the car door is there, we'll deal with what happens if the car door isn't there in just a second. Okay? Assuming that the car door is there, here's what Vanessa is going to feel. If I say, Vanessa, what happens? She says, oh, Mr. Burkamp, oh, man, I felt like I was being pushed up against the car door. Okay? So, in that situation, what you feel is what we call centrifugal force. Okay? So, centrifugal force means outward seeking. So, if you're Vanessa, you're going to feel like there's some force inside the car pushing you against the door. But this is where logic fails you. Okay? This is where logic doesn't make any sense. Because if there's actually a force pushing you against the car door, okay? Here's what would have to happen. The source of the force would have to be somewhere inside the car. And it's invisible. It isn't like, oh, here's my centrifugal force machine, and you can see it inside your car. Okay? It's invisible. Not only is the source of the force invisible, when it emits this force, it's also invisible. It isn't like, oh, she's turning. We'll watch the wave of force push against her. So it's invisible. When it interacts with her clothing or skin, that's invisible, because it isn't like you see like the hand of the centrifugal force god pushing against you. It's like, oh, okay. So it's invisible. The interaction is invisible. And this machine only works when you turn. If you're just, it isn't like I'm going to be driving down the road and all of a sudden, bam, I start being pushed against the side of the car, which would be really weird, okay? So not only does it only operate when you turn, it senses how fast you're turning. So if you're turning really fast, it goes, oh, I'm going to push harder. Or if you're turning in a really tight turn, it's like, oh, I'm going to push harder, okay? No. Now, visualize a different scenario. We won't do this because we like you.
It's dangerous.
But imagine that she's driving her Jeep, okay, and there's no door. Okay, we have taken the door off. There's no door. The seats are frictionless.
Oh.
Frictionless seats. And there's no seatbelt.
Oh. This feels like a golf cart.
Oh, kind of is, right? Death trap. So, imagine this. Now, we're up in a balloon looking down watching this. Okay? If you're up in the balloon watching this, you're going to see the Jeep or the golf cart or whatever turn out from underneath her. That car is going to turn and go like this. We're up above. What are we going to see Vanessa do?
Just go straight.
Vanessa's just going to go in a straight line. Okay? Because she has mass, because she has inertia, she's going to continue to move in a straight line. Because there's no force to make her velocity vector change. So what happened yesterday with the golf cart was just that scenario, right? Now, this is why you feel like you're being pushed against the car door. Because your body, what does your body want to do? Your body wants to go in a straight line. So you're feeling the car door pushing against you. And you feel that action-reaction force. Just like if Jackson was sitting here, and I came up from behind him and I pushed him forward. So this is what Jackson would do. Jackson would go, oh, like this, right? So I push it forward. Jackson would be like this. He'd go, oh, right? Okay?
Do it, Jackson.
No. But is there any force in front of Jackson pushing him back? No. What does Jackson want to do? stay at rest. Now, we won't do this, it's because we like Jackson, okay? But imagine that Jackson's head was severed and was on rollers,
Oh,
okay? We won't do this, we like you, okay? And I walk up behind Jackson and I push him really hard. What would his head do? It would stay right there, his body would accelerate out from underneath him and his head would go quick, just like this, okay? Now, this is why, trust me on this one, when you get in your car today, make sure that your headrest hits you in the middle of the head, okay? Because in my spare time, I do crash analysis for lawyers, and whenever there's a neck injury, it's because of the fact that they didn't have their headrest in the right position. Because what happens is that you accelerate the lower portion of your body, because that's attached to the seat. But then your head isn't anything here, and then that stays at rest, basically, and your body gets accelerated, and then that stretches your tendons and everything through here and your ligaments. That's what causes whiplash. So when you get in your car today, make sure your headrest is kind of right up here. So in case you do get rear-ended, that you don't run into a situation like that. And that is keeping your head from having a different acceleration than the lower part of your body. Okay. So, we need sources of centripetal forces. Okay? So the one that you deal with most often when you drive is friction. Okay? All right? So when you drive, you turn your steering wheel, assuming that there's friction, there you go. Or when you're walking, okay? I walk this way and then I turn to go out the door, okay? Excuse me, there's a certain amount of friction between my shoes and the floor, I can make the turn. So, let's say that let's say it's the winter time, and here's the intersection of 21st and Mays Road. And Vanessa's headed south on Mays Road, and she wants to take a right and go west on 21st Street. Okay, so she's coming down like this, right? Turns the steering wheel, the car turns. Under normal circumstances, the friction between the car tires and the road is what's going to provide that force, okay? And oddly enough, that force is going to act inward, okay? And that's what's going to allow that to happen. However, let's say that we've had a massive ice storm, okay? And everything is just a sheet of ice. No friction whatsoever, okay? And she's driving down the road, and she's got to make this turn.
that's happened to me.
Now, I know I'm going to go old school on this one, but I'm assuming most of you have seen, or at least are aware of, the Indiana Jones movies.
I've
Know what
heard
I'm
of it.
talking about?
Yeah.
Okay. What does he always carry with him?
A whip.
A whip. So, Vanessa's going to do the Indiana Jones thing, okay? So there's a telephone pole right here at the corner, okay? So she's going to take that whip, wrap it around the post, and then hold on to it, and that's going to slingshot her around. So the second thing you can use is tension, okay? So that's what we're, like in the lab that we're going to start on Monday, or when I swing that rubber stopper around over my head.
Tuesday.
Huh?
Tuesday.
Tuesday. Yeah, we don't have school Monday, Tuesday.
Oh, yeah.
So long. So as that, we're going to use just like I did with that rubber stopper. So the other thing that we can use is a chain, a string, something like that. Now, here's the third option. So let's go a little bit on a bigger scale. Here's our star, otherwise known as the sun. And we're on this rock that's going around the star.
Nice.
Is the Earth accelerating right now? And that's a good thing, okay? Are we falling towards the sun?
Yes.
Yes. Because if we're not falling towards the sun, we're screwed, okay?
Wait.
So, as the Earth goes around the sun, it's accelerating. Because the direction of that centripetal acceleration is inward. Because at any given instant, what does the Earth want to do? Earth doesn't want to travel in a circle, the Earth wants to travel in a straight line. So if we ever lose gravity, the sun says, you know,
I don't like you anymore.
I'm done. We've been together a long time, I'm over it, I'm sorry, I'm gonna cut you loose. It's gonna take us about 8 minutes to figure that out, because gravity travels at the same speed of light, okay? So about 8 minutes, we're gonna go, see ya, just like that rubber stopper. We're gonna go off in a straight line.
Maybe
And
dead.
we're gonna get awfully cold, and we're gonna get awfully fast, okay? And awfully dark. So we're gonna go like this. So it's a good thing that we're accelerating towards the sun, because the alternative is that we're not, and then we're not going to exist for long because we're out of here. So the third thing we can use is gravity. So imagine this. Vanessa happens to have in her car a bottle of Acme dehydrated black holes.
No.
Just add water. So as she drives by, she's gonna throw out one of those little tablets and it's gonna land right there in the corner. She's gonna add a little bit of water to it, and it's gonna instantaneously create a very intense gravitational field. And that intense gravitational field is going to basically put her into orbit, okay? For just a little bit. And then, once it gets to this point, then it's gonna disappear, and then she can go about driving. So those are the 3 ways that she can make that turn. Friction, tension, gravity. Now, the other option, I don't recommend this, is that let's say Vanessa calls up all her friends and says, hey, I gotta make this turn. But it's a sheet of ice, okay? I'm out of Acme dehydrated black holes, I can't use that. My bullwhip broke, can't use that. So how could she use her friends to make that turn?
Everybody leans tension.
Well, tension, basically you would form like a wall.
A human
Right?
centipede.
So, huh?
Human centipede.
Yeah, basically. Now, here's the deal. So as her friends are gonna help her make this turn, what are her friends gonna do? Push her to the outside or push her to the inside?
Inside.
They're gonna push her to the inside. So you all would line up and go like this and push her towards the inside. Because what does her car want to do?
Keep going straight.
It wants to keep going in a straight line. So this is why centripetal force and centripetal acceleration always acts inward, okay? Because you always want to go in a straight line. Now, let's talk math.
Yeah.
Yay.
Yay.
So the simplest way to calculate centripetal acceleration is v squared over r. Now, here's the deal. Let's look at the units. That velocity is oddly enough going to be in,
Meters per second.
but that's going to get squared, then I'm going to divide by the radius in meters. So I get meters squared over seconds squared divided by meters. Miracle of miracles, I get
Meters per second.
squared, which is what centripetal acceleration is measured in. Okay? So that's the short version. Now, just like F equals mass times acceleration, oddly enough, centripetal force equals mass times centripetal acceleration. What was that? Okay? What that means is that we can write that as mv squared over r. Oddly enough, we have kilograms times meters per second squared. We get newtons. There we go. So if you know how fast the object is moving, and you know the radius, plug and chug type thing. Now, if I double the mass of the object, Devin, what's that going to do to my centripetal force? It's going to double it. But what if I double my velocity?
Gonna quadruple it.
Then it's going to go up by a factor of 4. What if I double my radius? Then it's going to become half. So what this means is that centripetal force is directly related to mass. It's directly related to velocity squared and inversely related to radius. So as radius gets bigger, centripetal force gets small. Mass gets bigger, centripetal force gets bigger. Okay, now stop that for a second.
Probably shouldn't start. Now we are.
Okay. So here's the deal. I'm going to take a couple of quarters and I'm going to put it here on what is known as the green spinny thing. It has a screen and it spins. Not the most creative name in the world, but you get the point. Okay, so I have the green spinny thing. So I'm going to get this thing spinning like this. Okay? Now, are the quarters accelerating?
Yes.
Yes. How do you know?
They're moving away.
Well, what are they not moving in?
Straight line.
They're not moving in a straight line. They're moving in a circle, right?
Yeah.
So that means there has to be a certain amount of centrifugal force. So if we're going to calculate that, let's look at this idea. So if I take this rubber stopper, I'll do it here where you can hopefully see it. Okay? I've got this rubber stopper going around like this. I want to calculate, listen to me very carefully, the speed of the rubber stopper. So what can I do to figure out the speed of the rubber stopper? What are two things that I can measure to calculate speed? Well, hold on, what'd you say?
The acceleration.
No, I'll get to the acceleration.
Period.
I can measure period, right? I can measure how long it takes for it to make one revolution. What else could I measure? How can I figure out how far it goes in one revolution? Measure the circumference. Keaton's back there giving the international symbol for, measure the circumference. So, if this thing is going around like this, what can I measure to determine the circumference?
Radius.
Oh, radius, right? Oh, I can measure the radius. So, Beckham, knowing the radius, how can I find the circumference of a circle?
Multiply the radius by 2.
Pi.
Fantastic. So what we're going to do is, this is going to look fancy. It's really simple. We're going to use the idea that velocity is distance divided by time. That's a horrible T. Distance divided by time. That's what we're going to do. But here's the deal. The distance is going to be 2 pi r, which is going to be, as Keaton put it, the international symbol for circumference. Okay? So that's going to measure the circumference of the circle. We're going to divide that by, listen to this, is going to be important. This is uppercase T, not lowercase t. So uppercase T is referring to period. How long it takes to complete one revolution. Okay? So we can use this, we're going to use this idea with planets as they go around the sun. We're going to use this idea with rubber stoppers as they go around in a circle. Okay? Now, on your equation sheet, you have this. That frequency is the inverse of period. So period is how long it takes to complete one revolution. Frequency is how many revolutions per second that it takes. Okay, now notice that these are inverses of each other. So if you visualize this, so this is me swinging the rubber stopper relatively slowly. Okay, so what that means is it's taking a while for that thing to make one revolution. But you're not seeing the rubber stopper go by very quickly. Now, if I make it go faster, now what happens to the amount of time for one revolution? It's gotten smaller, but what's going to happen to the number of revolutions per second?
Goes up.
It's going to go up. So this is why these are inverses of each other. So if you look at what happens with the units, this is technically seconds per revolution. We're only going to use this when things are coming back to the same point. Planets, rubber stoppers, things like that. So if you look at what happens with the units, if I take 1 over seconds per revolution, look what happens. The revolutions flip up and I get revolutions per second. Now this is why these are inverses of each other. So that's why if I go really slow, that's a relatively large period of time. But I don't make a lot of revolutions per second. Okay? Now if I go faster, period becomes much smaller, but frequency is going to go up. So if you look at like even our planets, okay, where's Mercury? It's closest. So it's going to have a short amount of time, only 88 days, to complete one revolution. But it's going to have a relatively high frequency. Pluto, which I still think is a planet, I don't care what you say, Pluto in my mind will always be once a planet, always a planet. So Pluto takes an incredibly long time to make one revolution. So it's going to have a very small frequency, okay? This is why these are inverses. So here's where a little bit of magic happens. So we can say velocity is 2 pi r over t, but period is equal to 1 over frequency. So I can also write this as 2 pi r over 1 over f. All I did was substitute 1 over frequency for period. So, but when I divide by 1 over f, what happens? That's the same as 2 pi rf. Okay, so if you look at the units, this is meters divided by seconds, right? Circumference divided by time, meters per second. This is meters times 1 over seconds. I still get meters per second. Now it's even time for more voodoo. So we said centripetal acceleration, and this is kind of the pirate unit because we're going to have a lot of R's. So I got acceleration is v squared over r. But we just said that velocity was 2 pi r over t. So I'm going to substitute in 2 pi r over t, and we're going to square that, and then I'm going to divide it by r. Okay? Now, listen to me, but watch this very carefully. What do I get when I square this whole thing? 4 pi squared, r squared over, divided by r. Now this is cool because the pilot's going, r, I got r squared. But unfortunately, what's going to happen? Oh, I'm going to lose one of the r's. So I get 4 pi squared r over t squared. Wait for it. Look at what happens to the units. I got meters divided by second squared, which gets me acceleration. Woo, yay for units. Okay? But wait, there's more. That sounds like an infomercial, but wait. For an additional $1.99 in shipping and handling, we will substitute in 4 pi squared r, but instead of over t squared, what can we put? 1 over, but it's going to be 1 over f squared, right? True? So then I'm going to have 4 pi squared r over 1 over f squared. What's going to happen to the f squared? It's going to flip up, and I'm going to get 4 pi squared r f squared. Ooh, that's fancy. So here's the deal. I still get the same units because that radius is going to be in meters. That's going to be 1 over second squared. I get meters per second squared. Hey, I get acceleration. So there's 2 ways you can do centripetal acceleration. 3 ways. You can use v squared over r. That's an option. You could use 4 pi squared r over t squared. Or you could use 4 pi squared r frequency squared. Same thing. You get the exact same units. Now, back to the quartas. Okay, back to the quartas. Look at this scenario. These 2 quarters are going to go around like this. Which quarter takes the longest amount of time to go around? The outside quarter? The inside quarter? Or do they take the same amount of time? Same amount of time. Okay? Period is the same. Because if Vanessa is timing the outside one and I'm timing the inside one, we're both going to get the same amount of time. Are they both traveling at the same speed?
No.
so.
You think so?
Yeah.
Well, let's look. V equals 2 pi r over t, right?
Mhm.
Is t going to be the same for both quarters?
Yeah.
T is going to be the same for both quarters. T is the same for both quarters. So as radius gets bigger, what happens to velocity?
Increases.
So think about this. The outside quarter has to travel a greater circumference in the same amount of time as
Oh.
the inner one does.
Mhm.
Okay? Makes sense.
Yeah.
Or imagine that you're in a walking band, okay? And if you're out here on the edge and you're in a walking in line in the band and you're trying to walk around in a circle and maintain the straight line, who's going to have to walk the fastest? The person on the outside or the person on the inside?
Outside.
Person on the outside, because they have to travel a greater distance in the same amount of time. Now, here's the next big question. I'm going to make this thing go spin up faster and faster and faster. What's the source of the force that's keeping the quarters on the table? Friction. Okay? There's no strings. Okay? I don't have strings attached to the middle. There's not a gravitational source here in the middle that's keeping them in orbit, which would be cool. Okay? So there's friction. Now, let's look at that in a little bit more detail. So if I draw this out, here's the quarter, right? So, and this is as it's moving. So what are the three forces acting on the quarter? There's three of them.
Friction.
Friction, which is going to act which way?
Towards the center.
Towards the center, right? And that friction, oddly enough, is going to create my centripetal force. Okay? What else you got? Acting straight down, and then you have your... Now, do you have an imbalanced force? Yes. Are you going to have an acceleration? Yes. Okay. Now, does mu equal force friction over force normal?
Yes.
It better. This has changed. Okay, I didn't get the memo. Could have, but I don't think so. So we're going to do a little bit of magic here. The frictional force is what's creating the centripetal force. True? Cool with this. So instead of centripetal force, I'm going to put my centripetal force there. Okay? Okay, I can do this. That's what's creating it, right? So now, instead of my normal force, what am I going to put? Gravity, right? Now, here's where the magic happens. How can I calculate my centripetal force? What two things together, simple things, can I multiply together to get my centripetal force? Mass and my centripetal acceleration. Simplest way to do it?
Yeah.
What's the simplest way to calculate the weight of an object? Mass times my
Gravity accelerator.
gravitational acceleration. Oh, look, masses cancel out. Oh, look, it's a ratio of my centripetal acceleration to gravity. So here's what's important. The mass cancels out. Okay? Mass cancels out. So this is going to be my coefficient of friction. So what this means is the one that friction is a limited amount of force. Okay? It's not like this all-knowing, oh, friction will provide everything that we need. Okay? There's a limit to what it can do. So with that said, this is why I want you to think this through. I want to make this thing go faster and faster and faster. Okay? Which quarter is going to fly off first? The outside quarter, the inside quarter, or they're both going to fly off at the same time because they both have the same period. So outside, inside, same. So how many vote? Same. Inside? Outside. Everybody's on the outside train. Why?
It's closer to the edge.
So what? It's closer to the edge. Truer words have never been said. It's closer to the edge. Where does closer to the edge play into this equation?
The circumferences, or has a bigger circumference, or a bigger radius, my bad.
Has a bigger radius, so what?
it needs more speed, so it should fly off faster, or first.
Okay? So let's see what happens, first of all. You ready? So go faster and faster and faster. The outside one flew off first, right? So there's a limit to what friction can do. So if you look at this idea, if you go back to this mu, that mu value is a fixed value. So basically, once the needs of the centripetal force is bigger than the frictional force that it can provide, it's going to fly off. Just like I am not going to take Hank and a thin piece of thread and try and swing Hank around over my head. It's not going to end well, okay? Because we can just go boink and tear this. So this doesn't provide very much, isn't capable of producing very much centripetal force. So as soon as that need would exceed the thread, gonzos, right? So the same thing is going to happen here. That friction can only provide so much force. And so once the need to move in a circle exceeds that value, Mother Nature goes, see ya, I've done my work here, I can't do any more, go away, okay? And the quarters are going to go flying off. So this is why the outside quarter flies off first, because it needs more centripetal force, because if you look, the simplest way to look at it is that centripetal force equals mass 4 pi squared r over t squared. So is the period for both quarters going to be the same? Yep, that's the same. Mass is the same, right? So as the radius gets bigger, what happens to the needs of the centripetal force? It also gets bigger. Okay? Got that. Okay. So stop that. Hand out your. So let me talk about, and yes, this is one of those answers on the left, work on the right. Okay, draw the line. Okay. So let me talk about multiple choice question number 3. So toy airplanes traveling in a circle is made to go faster as more wires played out until both the speed and the radius of the circle are constant at double their original values. We want to look at what's going to happen to these different things. So there's 2 ways you can do this: smash mouth physics, elegant. Which one do you want to do first?
Elegant.
Elegant? Okay. So you're talking about velocity and you're talking about radius. So I'm going to look at the fact that centripetal acceleration equals v squared over r. So that's my initial setup. I don't care what the velocity is. I don't care what the radius is. It's v squared over r. Now, when I look at my new acceleration, AC prime, my new centripetal acceleration, so I'm going to double my velocity. So how am I going to write that? 2v, right? But that's going to get squared. So it's going to go twice as fast. But what am I going to do to the radius? Nope. It's going to get doubled, because I'm going to double my radius and I'm going to double the velocity, right? So this is going to become 2r. So when I square this, I get 4v squared over, excuse me, over 2r, and that reduces down to over r. So what's going to happen to my centripetal acceleration? It's going to double. Okay, so that's their elegant approach. Some people like this. Some people hate this process, loathe it with its very being. Okay. So the other way you can do this is smash mouth physics. So what's an easy velocity to choose? 1. Okay. What's an easy radius to use? 1 meter. Oh, that gets an acceleration, oddly enough, of 1 meter per second squared. Simple. Okay. Now I'm going to look at AC prime. Okay. So I got 1 meter per second. So instead of 1 meter per second, I'm going to use 2 meters per second. But that's going to get squared. And then instead of 1 meter, I'm gonna use
2 meters.
2 meters. So I get 2 squared, which is 4 meters squared over second squared divided by 2 meters. I get,
2 meters per second squared.
which is
Exactly.
double my original value. Okay? So, I don't care how you do it. Okay? It just has to make sense to you. Okay? It just has to make sense to you. Now, when you get down to number 9, problem number 9. So, centrifuges, we use them in chemistry. Basically what they do is they create false gravitational fields. And we put test tubes in them and it spins really, really, you might have seen it in Chem 1, okay? They spin really, really, really fast. So what you have there is 5,000 revolutions per minute. So 5,000 revolutions per minute. Sometimes you see it written as 5,000 RPM. So if you've seen, like, some of your cars might have called a tachometer, which shows you how many revolutions per minute your car is going. That's what that stands for, is revolutions per minute. How many revolutions per minute does your engine go through? Okay, that's a short version. So with this one on number 9, so this is going to spin at 5,000 revolutions per minute. So if you're going to do this, there's a couple of ways you can do this. One is that you can change that 5,000 revolutions per minute into revolutions per second. Okay, so you can take 5,000, divide that by 60, and then you've got revolutions per second. So what we're looking for here on number 9, you want to find the centripetal force exerted on a giant amoeba at the bottom of the tube. So this test tube is going to be like this, and you're going to try and find this. So you need centripetal force equals mass times, and here's your choices. You could use mass 4 pi squared r over t squared. Now here's the deal though. You have revolutions per second. Okay? Is revolutions per second frequency or period? That's frequency. So if you want to use t instead of revolutions per second, what would you have to do? Flip it and take the inverse of it. So if you're old school is like Bergkamp, I like t squared. I'm happy for you.
F squared.
Okay? So you take 60, and divide that by 5,000 and put that in there. So if you like t, go, hey, t's for me. Good. There you go. That's what you need to do. But if you go, oh, Bergkamp, I don't like fractions. Okay? I'm more of a 4 pi squared r f squared kind of physicist. Okay, this is actually a little bit easier because all you have to do is take 5,000 divided by 60 and slam that number right into there. That way you don't have to take the inverse of it. On a problem like that, I don't care which one you do, just pick one. Now, when you get to number 11, 11's kind of going to go old school. So imagine that you're swinging a rubber stopper over your head like this, and you're going to let go of it. So on number 11, you got to go old school. Projectile motion is like a lemming problem. Okay, so just keep that in mind. When you get to number 10, let me kind of paint you the picture of what's happening on number 10. So here's the centrifuge. The test tubes are in here at a 30-degree angle with respect to the vertical. So this is a 30-degree angle, and this distance here is 5 centimeters. So imagine that. So imagine here's the centrifuge, and this test tube is in here like this at a 30-degree angle. So what you're going to have to do is find the distance from the center of the centrifuge, which is 5 centimeters to here, and then you have to add in the additional distance to get to the bottom of the test tube. So you got 5 centimeters. You're going to have to do a little bit of trig. This is a 30-degree angle. This is 100 millimeters. So there's all sorts of things going on here. You got to pay attention to the units. you gotta end up with this distance. So you gotta take 5 centimeters and add that to this side of the triangle so that you know the distance from the center spin of the centrifuge out to the bottom of that test tube. Okay, I'm done. You're on your own. So
Oh,